Hi guys, my name is Davide and I would like to welcome you on this visit at the ALBA Synchrotron. I'm a telecommunication engineer and I've been working here since 9 years now, I think, yes, as a staff engineer in the LINAC group. So, why are you here and what is ALBA and what is a synchrotron facility? So, synchrotron facility is a facility that produces synchrotron light. The synchrotron light is a very interesting properties of electrons that when they travel to a velocity, to a speed close to the speed of light, and they are bended, produce photons that can be used to study the molecular structures of the materials. This has thousands of applications in all types of science, like material science, chemistry, biology, and even cultural heritage. And this basically is what is this building behind me. It's a facility that produces this kind of light. We are funded by the Spanish government, by ALF, and the Catalonian regional government, La Generalitat de Catalunya, by the other ALF. So this is a quite nice example of cooperation between central state and the regional government. There are about 50 synchrotrons around the world, 20 of them are in Europe, and ALBA is the one and only that we have in Spain, which brings us in the state-of-the-art technology for this kind of machine. There is a third generation synchrotron light, and we are planning actually an upgrade to a fourth generation synchrotron light. So the upgrade will be called ALBA 2 and should take place starting from 2030. So fasten your belt and enjoy the visit. Hi guys, our first stop for today is the general screen machine status. Basically, this screen you will see several of these screens around the installation, and this screen shows us the basic information that every worker here, like engineer or beamline scientist, would like to know when they first get to the office. So we will see the beam current in the storage ring. Today is 0 because it's a shutdown days. A snapshot of the beam in the small blue rectangular square, the electron beam size, and the time that and the missing time for the next injection, and the efficiency, and the injection efficiency. You will also see in this black box a graph that shows you the storage ring current versus time, and last but not least, the number of beam lines that are receiving light at that moment. We have now, just to point you out, that we have now 12 beam lines under operation and 2 under construction and design phase. So now let's go inside to the heart of the accelerator. And we are now literally walking above our accelerator complex. Why do I say accelerator complex and non-accelerator? Because ALBA has 3 accelerators. A linear accelerator, which is the first one where everything began, a booster that ramp up the energy from the exit of the LINAC up to our final energy, which is 3 gigaelectron-volt, and finally the storage ring. But where we are now? So this bridge, where I'm standing on, divides the experimental hall and the service area. The experimental hall is where the beam line stands, and if you see here, like this blue one, where I'm on, is a beam line. And there, the white one, the purple one, and so on and so forth. As I said, we have 12 beam lines actually in operation and 2 under construction. And if you came here and zoom there, you see that yellow metal on the block on the wall is where the synchrotron lights came out from the accelerator. I didn't mention that we are right now above the accelerator, which you can see our tunnel is just behind these concrete blocks. And why do we need concrete blocks? Because, well, my colleague Judith will better explain you everything about that, but let me tell you that this is a safe machine and these concrete blocks are for shielding reasons. So we are perfectly safe in walking here, and because the concrete blocks shield us from possible radiation that the beam can produce. I won't stay longer here because we will go inside the tunnel and you will see with more detail and with great things everything that we are talking about. And we're now going inside the service area, leaving the bridge and towards the LINAC. I don't know if I said that to accelerate electrons, we need radio frequency. And now we produce this radio frequency. To produce radio frequency, we use amplifiers that are the one that you are seeing now, just behind me. And I don't know if you can see there. So the red cupboard are where the amplifier stands, then that produce the RF power. Then you have a power combiner, and then you have these waveguides that literally guide the RF power inside the tunnel towards the RF cavities. But we will explain this later with more details. The other things that you see now are all these black racks, where basically there are servers, there are power supplies, there are controls, PLC controls, and so on and so forth. Then in the service area, you have several labs. This one is the power supply labs, where basically they do test experiments or they repair faults when some issue happens to some power supplies. And against controls, racks, and against another RF stations where the RF is generated. And here you see an access to the storage ring, so another door. And again, racks is basically a lot of cable and data storage devices. And finally, we get to the LINAC service area. Here you see two klystrons that are, again, RF amplifiers, different from the one that we saw before. This one works at 3 GHz, but we will see in a very little time. And we are now in front of the LINAC. And now we can enter the LINAC. LINAC stands for Linear Accelerator. And remember that today we can enter because it's a shutdown days. So it's totally safe, the machine is off, and we can enter without any risks. Do you remember the big concrete blocks that I was talking to you before? So they're this thick. It's more than 1 meter. So we are completely safe against radiation. Inside this cabinet, that is a 90 kilo electron volt, so it has a big risk of big electric risk. There is the cathode, where everything starts. The cathode basically is a piece of material that is heated up to 1,000 degrees and generates a cloud of electrons that are then ready to be accelerated. It's covered, but here we have an example of an old cathode that we use in operation first. So the electrons here are generated, and the very first acceleration is electrostatic acceleration. So due to potential differences among the generated electrons and ground, which is 90 kilo electron volt, that makes the electrons start moving. Before being accelerated, the electron needs to be bunched, because we cannot accelerate single particle. We can only accelerate bunch of particles. And they are bunched through the bunching system, which is this blue cavity here, which is basically 22 consecutive cells, radio frequency cells. The energy of electrons when they leave the cathode until the entrance of the buncher is about 90 kilo electron volts. At the exit of the buncher is already 16 mega electron volt, which is very close to the speed of light. So the electrons in already less than 3 meters reach a speed and an energy close to the speed of light. Then they are furthermore accelerated with these two, this one and the other one, accelerating cavities, which basically bring the electrons up to 70 mega electron volt and up to our final energy of about 100 mega electron volts. The RF inside this cavity came through these waveguides. Do you remember that the waveguide that we showed you before, the one from the other accelerator, from the booster, from the storage, they were bigger? Why? Because we work at 3 gigahertz, which means that the wavelength of our radio frequency wave is shorter with respect to the one of the other accelerator, which is 500 megahertz, so it's 6 times more. So we are here walking through the end of the LINAC, and something that I didn't mention, that inside this, all this is in vacuum. And we are talking of a vacuum of about 10 to the minus 9 millibar. So very, 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 very almost no particle of anything inside there. The vacuum is generated through in this section of the machine, through 9 ion pumps that are particular pumps used to generate vacuum inside the tube. After the LINAC, we have triplet sections, quadruple section with 3, so it's a triplet that we use to focus the beam. And this green one are dipoles that we use to correct the beam position in vertical and horizontal. Coming through the end, we have a dipole. A dipole, basically, it's a magnet that you use to move the beam in the horizontal direction. So this dipole has 2 exits, one at about 8.5 degrees and the other one at about 30 degrees. The one at 8.5 degrees go through, so in this direction, through the booster. And the other one at 30 degrees go through inside this, which is a Faraday cap, basically at the end. So this is a diagnostic line where we used to make experiments to prepare the beam for operation and so on and so forth. As you can see, even here the shielding is very important. And like here we add this lead block in order to improve the shielding in this area because the radiation generated by the beam shooting the Faraday cap was quite high. And then going from there, so behind that wall, we will access the storage ring and the bunker tunnel. Here we go. We're now literally on the other side of the wall. Before we were there, behind that wall, inside the LINAC tunnel, and now we are in the storage ring and booster tunnel. And what we are seeing is the LINAC to booster transfer line, where we see another dipole, some corrector, some quadrupole to focus the beam, and this line basically join the exit of LINAC accelerator to the booster, whereas our beam is then accelerated from 100 megaelectron volt to our final energy of 3 gigaelectron volt. The join, so the interaction between the LINAC beam and the booster is done by pulsed magnets, which is called kicker. That basically the main function is to kick the beam from this direction to this direction. And we move just a few meters downstream with respect to the point where we were before at the exit of the LINAC. And now we are here where you can see on my right the booster accelerator and on my left the storage ring. So remember, the beam that exits the LINAC has an energy of 110 megaelectron volt. Then goes inside the booster where it's ramped up to an energy of 3 gigaelectron volt, which is 99.999, a lot of 9% of the speed of light. But how thick is this beam? It's very, very, very thin. So you can see here, this is the beam pipe where the beam is circulating, and the beam itself has a thickness of almost a hair for the one who has, not my case. Once the energy is, the final energy is reached, the beam is then kicked up with the same type of magnet as before, kicked up from the booster to the storage ring. Through this again, booster to storage, transfer line. And now we see on my left, the storage ring. What did we say before? We said that we use the electric field to accelerate the beam. So radio frequency to accelerate the beam. But how do we keep the beam out in the trajectory that we want? So how do we bend the beam and how do we focus the beam? Well, with the magnetic field. So the main components of this part of the accelerator are magnets. Which kind of magnets do we need to keep the beam in a circular trajectory? By the way, I didn't say that the booster circumference is about 250 meters and the storage ring circumference is about 270 meters. So, coming back to us, what do we need? We need magnets to bend the beam and focus the beam. Which type of magnets, how many types of magnets do we use here? We use mainly 3 types of magnets. The bending magnets, which are this big red one that are used to bend the beam, which are basically dipoles. The quadrupole magnets, so they are quadruples, as the name says, that are mainly used to focus the beam. In order to avoid, so the beam is charged particle of the same charge, so they feel the Coulomb space force, so they tend to repel themselves. So we need to keep them focused. So this quadrupole effect is used to fight the Coulomb, the space charge effects, and to keep the bunch in such a dimension that are good for us. And then that we have the sextupole magnets, so six magnets that are used to compensate the unwanted effect that dipole magnets and quadrupole magnets generate inside the beam. Another thing that you can say here are these tubes that are basically water tubes. And why do we need water in this kind of accelerator? Well, because the magnets at the end of the day are just copper where an high intensity current work through. So when the current is inside the magnet is heated up, and we don't like this, because if the magnet is heated up too much, then they will lose the magnetic field properties, or it will change at least the magnetic field properties. So we need to keep at a constant temperature, and that's why we use demineralized water to cool the magnets down. And here are all these small white tube, this big orange tube. So they are all vacuum tubes. And these one are flow meters, so to constant monitor the water flows. And I didn't mention that we have 32 so this block is a photo period, focus in the focusing period, and we have 32 along the machine to keep the beam in our wanted trajectory. And now we are going to go where the beam exits the tunnel through the experimental area again, where actually the light is then delivered to the beamlines. We have now our electron beam, millions of electrons circulating at almost the speed of light, 3 gigaelectronvolt, 99.999% of the speed of light, inside our storage ring vacuum pipe. And remember, every time that the beam bends, it produces synchrotron lights in forms of photons, all right? But this also causes some energy losses of the beam, because energy transformation. Remember that in nature, nothing is destroyed, but everything is transformed. In order to restore the beam energy and to keep the acceleration constant, we need radio frequency, so electric field. And how do we provide the electric field to the beam? Well, we have here the radio frequency cavity, which has this triangular shape. What do we see here? So the radio frequency is delivered from outside the tunnel through this big waveguide system, and it arrives here into the cavities. Remember, so we are in a synchrotron machine. What does it mean, synchrotron? It means that the electron beam that is circulating at speed of light and the radio frequency that then is spread inside the cavity must be synchronized in order for the beam to be accelerated and don't lose too much energy, making turns and turns and turns. All right? So that's why the RF is very, very important. And the synchronization between the beam and the RF is even more. Well, now, if we move forward towards a beam line, we see an insertion device. What is an insertion device? It's basically a bunch of, it's a magnets, where in this case are a lot of small magnets with inverted polarity, so positive, negative. And when the beam passing through it generates, so it is bent, and the synchrotron lights, so the photons, are generated. Now, if you come with me, I want to show you where basically the photons exit, let's say, the storage ring and enter inside the beam side. And now here it's a bit tight. There we go. Luckily, I'm in shape almost. So you see, See the purple things behind there? So it's an insertion device. See another beam pipe starting from there. And here we are again at the yellow windows that we also saw before at the very beginning of this video at the bridge. And behind this wall, there is a beamline. So just to recap, we have there the booster that boosted the energy from 100 megaelectron volt to 3 gigaelectron volt. The storage ring. And finally here, a beamlines where the photons are. And we are now outside again, outside the concrete block where before we were just there, just behind this white wall when I was showing you the beamlines, and inside of course the concrete blocks. And we're now walking through the control room because I mean everything that you have seen so far is mainly inside the concrete block or down there in the service area, so it must be remotely controlled. So that's why we have a control room where the accelerator division, people from accelerator division, but not only, works in order to deliver to the experiment the best beam, the best photons that we can have. So with high brightness, high intensity, and with all the other good properties of photons and electron beams has. But what kind of person work in ALBA in general in this facility? So basically we're a person from all over the world. First of all, where I'm Italian, I apologize for my accent, and from other all specialities. As I told you, I'm an engineer, but here we have chemicals, physicists, like my colleague Judith. She's a physicist, well, very good one also. And also the technical part, and well, last but not least, the administrative part, which makes all this working. So, well, okay, a control room is basically just a bunch of computers where a lot of GUIs, graphical human interfaces, to control the beam, all the beam parameters that we have. And, okay, today there is nobody because we are in a shutdown days. And we control, well, through beam position monitor, we control beam position, beam charge monitor, we control the charge, radiation level, and vacuum, and really everything. And here we have our operation calendar. So, well, I didn't mention so far, but this machine basically runs 365 days per year, 24/7. Of course, we have some breaks, so our runs times runs last more or less 1 month. Then we have 1 week of shutdown, the one that started today, and then we have machine days in between. And in total, we deliver about 6,000 hours of light for users per year. And I think that is all from my side. Now I leave the stage to Judith, which will show you all the beauties of experimental beamlines.
So, we are now back to the experimental hall of the ALBA Synchrotron light source. Now you know much better how the accelerator complex is working, and now you know that the electrons are accelerated almost to the speed of light. But don't tell Davide, but actually what we are doing with the electrons is just farming them. We are just farming very fast electrons so that they can deliver their product, which is called synchrotron light. And this is what it is radiating. The electrons are radiating light of a particular characteristics, which is called synchrotron light. So now, the electrons are just turning around and around, but the photons just go through a straight line, of course, because they are not affected by magnets, and then simply go through the cage of the accelerator complex. And you can see down there a yellow window. The upper window is just an alignment one, just an alignment window. But down the bottom window is where the photons go out of the accelerator complex, and they can be used to do experiments. So now, of course, these photons need to be adapted. And you need to prepare as well the sample environment for the experiment to be done. And this is done in the beamlines. You can see all around the experimental hall many beamlines. You see here a beamline painted in white and blue. Then later on you can see a purple beamline, and so each beamline is an experimental station specialized in a particular type of experiments and a particular type of samples. The nice thing of the synchrotron light is that it covers a whole spectrum of wavelengths, that is, of colors. And then you can adjust the color to the particular needs of your experiment and of your sample. And this is why the synchrotron light has so many broad applications. Has also other good characteristics. For instance, flux, the number of photons that these electrons produce, and also the collimation. They are really directed so that it's easier for us to collect them and do the experiment. So no wonder that the synchrotron light is used in physics, in biology, in chemistry, in material science, in archaeology, in wherever you can imagine, can be used for can be studied using synchrotron light. So now, why is so important this synchrotron light as well? Because actually you have other kinds of lights, of sources. In this particular case, the important thing is that we produce a lot of X-rays. And X-rays have two very, very nice characteristics. First is that like Superman, they can go through the objects and see inside the objects. So we may be sensitive to the bulk as well to the interface of the things. And second, importantly, is that the wavelength, that is the period of the light, of the wave that is forming the light, is similar, commensurable to the distance between different the consecutive atoms. So in the end, we have contrast. The light that is seeing this atom is different from the light seen by the other atom. And this is why we can really go to atomic scale, to molecular scale, in order to study the materials, any material, and really, really deep inside to the atomic level. So now we know that synchrotron light is very useful for many, many applications. So now, how can research groups come here and do their experiments? Well, actually, there are two types of access. One is academic, that is for research centers, for universities, for whoever that has an interesting project. And the other type is just for companies, private companies, that they may use synchrotron light in order to boost their developments. So now, if you are a company and you want to use synchrotron light, our synchrotron light, you simply just pay by hours, typically 8 hours, and you do your research, your experiments, and then you analyze. Otherwise, if you are a university, a research center, a public institution in general, then, well, then you have to apply in the call for proposals, and then an external panel is finally selecting and scoring which are the best proposals. And depending on the available beam time, they get awarded beam time or they are in the waiting list. So now you see all around many, many synchrotron beam lines, many experimental stations, and now we are going to go to some of them. You can see here a beam line called Florea, actually, and actually is very clear here, the structure. You have first a first hatch, which is painted in green in this case. In there, you stop most of the radiation that is emitted by the storage ring and by the accelerator complex. And later on, you see a number of optical elements that are adapting, that are adjusting the synchrotron light to the particular needs of the sample and the technique we are going to use. Let's go to see more beamlines. So we are right now at the experimental floor, and we see here the LOREA beamline, which is a beamline specialized in a particular type of experiments on solids, on semiconductors, on different materials. But let me explain you element by element the whole beamline actually. And we are going to start, oops, careful. So we have to start from the beginning. And now we see here the first elements after the photons are leaving the accelerator complex. The products, that is the synchrotron light, is coming through this vacuum pipe here, and they find first the first mirror, which deflect the photons. The light that is not used then is stopped by these LED walls here. And we are just starting filtering the light. Then comes little boxes, which are slates, are beam diagnostics. And finally, we get the following element, which is the monochromator, in which we are selecting the wavelength, the particular color of the beamline, the experiment that we are going to use for a particular sample. So now, once the photons are filtered by their wavelength, and we have only one color, then we have the so-called monochromatic beam. And finally, we get more elements to focus the beam right down to the sample position. So this is the beam transport. These are slits that are just collimating and just filtering the beam. We have here more and more elements, and here in this box are the final mirrors in order to get the beam as small as a few microns. That is much less than the diameter of a human hair. And after these two mirrors, what we get is actually the end station. Oops, be careful as well. And the end station is where actually the experiment is being done. So this complex of instruments is where the three basic elements of an experiment are meeting together. One is the synchrotron light. Then second is the sample. And finally is the detector. You know what we are getting as an input. We know which is the output thanks to the detector. So knowing the input, knowing the output, we know what is going to, what's happening at the sample that is in between. So the sample is actually loaded here. You see here the sample holder at the tip of this metallic the instrument. Actually, this is in vacuum because the samples are very delicate, and the X-rays as well, they interact with air, and we want to have the cleanest experiment possible. So we have to get rid of the atmosphere. So that's why we have everything inside of vacuum vessels. So the sample is put here. Then it is transported to this chamber, in which is combined with other elements, etc., and maybe modified. And at the end, we have here the big chamber in which these three elements, the detector, the beam, incoming beam, and finally the sample, are meeting together. it's very difficult to see actually because very crowded. It is very crowded. But essentially, this is it. So, to be honest, you may think that the end stations are a complete mess. But you're not right, actually. Every single element has its purpose. You have here a valve, you have here a turbo pump, you have here a motor, there are more motors, more systems, etc. And aluminum paper. Lots of aluminum paper. It's not because we don't have garbage bins, whatever. It has actually a purpose. This aluminum paper is making the temperature uniform when we are heating the vessels in order to better evacuate and have a better vacuum. So in a sense, has the same function as when you are wrapping your sandwich for your breakfast. So we have the three elements of the experiment. We have the incoming beam, then we have the sample, and then we have the detector. And the experiment is actually based in an interaction between the incoming beam and the matter, that is a sample. Actually, there are three big types of interactions between X-rays, light, and matter. One is essentially microscopy. This is what we could also do with visible light. Then the other thing is, the other techniques is spectroscopy and fluorescence, in which we are really sensible to the energy of the photons. And finally, we have diffraction and scattering, in which we are sensitive to the dispersion, to the scattering of the light, thanks to the matter. So now, this is according to the techniques, but actually here the beamlines are really divided not in techniques, but rather in fields of application. Hola, ¿qué tal? In fields of application, I say. And actually, we have three big sections in which we are classifying the beamlines. One is electronic structure and magnetism. The other one is material science. The other one is life sciences. So we are right now in the middle of the two end stations of the CIRCE beamline, which is one of the beamlines of the electronic structure and magnetism section. Here we have the so-called NAP station, in which we are studying the chemical state of surfaces. And this is very relevant because actually in the surfaces is where the catalysis, the reactions occur. For instance, the reaction that allows us to extract hydrogen in order to be used in clean fuels, for instance. In the other side here, the second end station is called the beam, in which we are seeing the actual surface. And we are seeing, for instance, magnetic domains, and we are seeing how the surfaces evolve after and during the reactions. So in the first end station, we were seeing the chemical state. Here in the beam station, we are seeing the structure, the surface itself. So let's go for more beamlines. The second big domain of scientific applications is material science. And actually, this is the domain of this beamline, the MSPD beamline. Actually, you can see here that the instrumentation is enclosed in different hatches. This first hatch here is the optical hatch, in which we are enclosing the elements, monochromators, mirrors, that are adapting the synchrotron beam. Then we have the control hatch, in which we are controlling the experiment. And at the end, we find the experimental hatch, in which we are doing the actual experiment. We're enclosing everything in hatches because here the energy is harder. So the wavelength is shorter. And this could be harmful for us. So that's why we are setting up a LED hatches enclosure in order to protect us from radiation. So here Again, we are in the experimental hatch, and again, we have the same structure, actually. We have the sample here. Here, the sample holder is not actually right now in place, but we would have a sample holder, tiny sample holder, and the beam that is going through this vacuum pipe is finally hitting the sample, and the experiment, the interaction is detected by either this detector or this other detector. Here, we are studying materials like Siemens, for instance, or more importantly, very recently, batteries. We are improving our batteries of our mobiles or of our electric cars thanks to the research that in part is being done here at the synchrotron. And actually, not only batteries or Siemens or metals or alloys, we can do things like, for instance, paintings and archaeological samples and in general cultural heritage, because at the end, these are aged materials. So X-rays are very democratic. They don't care the origin, they do care about the matter, and they interact irrespectively of whether you have a teeth from the Pleistocene or you have the most recent battery that is going to be in place in the future cars. So now we are heading towards the last beamline I'm going to show you, MISTRAL, dedicated to the last big domain of the ALBA Synchrotron, which is life sciences. So in MISTRAL, we essentially have a big microscope in order to see the structure of the cells. But actually, it's not a visible light microscope, it's an X-ray microscope. So we can go through the cells and see inside the cells. We see the nuclei, we see the mitochondria, we see all the organelles that are forming the cells. And actually, this is important because the shape of the cell, the morphology of the cell, really relates to the function. And then we can study diseases, we can study infections, we can study how well the cells react after a treatment. For instance, in the case of hepatitis C, for instance, in the case of malaria, for instance, in the case of COVID, of course. We have studied all these diseases here. So essentially, we are just taking these cells, these whole cells, we are freezing them because otherwise they are going to be destroyed by the X-rays. And then we are inserting them inside the microscope, inside the sample plate. And then we adapt the X-rays. We make the X-rays interact with the sample. And we see the outcome at the synchrotron, at the detector, which is at the end of this pipe. So now again, we see finally an image of the cell. However, we see just a projection. In order to know the 3D structure, we are rotating the sample to get images at different orientations, and at the end to get the 3D structure of the cell. A cell in different conditions, before treatment, during disease, after treatment. And this is important for life science studies. Actually, the ALBA Synchrotron light source is not only visualizing cells, it's actually able to visualize individual macromolecules. For instance, DNA, for instance, individual proteins, protein complexes, and importantly, drugs that are attached to proteins in order to inhibit them and provide effective treatments. So ALBA is also helping in novel drugs to treat the diseases or to treat infections that we may have. And our visit to the ALBA Synchrotron light source comes to the end. You have heard a lot of new words, beamlines, accelerator complexes, but the bottom line at the end is that we are an X-ray microscope to explore the whole matter. Lot of fields, lot of techniques, lot of knowledge to be learned from ALBA. So I hope you enjoyed our visit, and I hope that if you want more information, you can follow us in our social media, Twitter, Instagram, Facebook, whatever you like, we are in there, and otherwise in our newsletter. Enjoy! Bye!